Hi everyone, now we are at sequences and series lecture number 4. So in today's class we are going to discuss about increasing and decreasing sequences and some related theorems. So here we go. First one, the decreasing sequence definition. Let an be a sequence of real numbers. Okay. Then the sequence an is said to be decreasing sequence if an is more than or equals to an plus 1 for all n belongs to natural numbers. It means, see, for example, let's take like this. So if you elaborate this, you will get this one. It means, so if you take n is 1, so it is a1 is more than or equals to, substitute n is 1, so a2, like this. And if you take n is 2 here, a2 is more than or equals to a3, that means a2 is more than or equals to a3, so like this. And a3 is more than or equals to a4, so a4 is more than or equals to a5, like this. So up to so on. So such a sequence an is said to be a decreasing sequence. So a1 is more than or equals to a2, and a2 is more than or equals to remaining all the terms, and a3 more than or equals to remaining all the terms, like that. So in this the highest term is first one, second highest term is second one, third highest term is third one, like this. Okay, such a sequence is said to be decreasing sequence. Similarly, the second one is increasing sequence. The sequence an is said to be increasing sequence if an less than or equal to an plus 1 for all n belongs to natural numbers. That means a1 less than or equals to a2, so a2 less than or equals to a3, and a3 less than or equals to a4, and a4 less than or equals to a5, and up to so on, like this. Okay, so in this a1 is the first lowest term, a2 is the second lowest term of that sequence, and a3 will be the third lowest term, like that. Second term is higher than the first term. Similarly, third term is higher than the second term. It means third term is higher than the both first and second terms, like that. So it is keep on increasing. That's why it is an increasing sequence. So next, monotonic sequence. A sequence of real numbers is said to be monotonic sequence if it is either decreasing or increasing. Decreasing or increasing. Let us look at this example. Let us verify which of the following sequences are monotonic or increasing or decreasing. Look at the first one. The first sequence, what are the terms of this sequence? 1 by n. The terms of the sequence are, so first one, if you substitute n is 1, you will get 1, n is 2, you will get half, n is 3, you will get 1/3, okay, and n is 4, you will get 1/4, and n is 5, you will get 1/5, and n is 6, you will get 1/6, and up to so on. So this is about the terms of the sequence. Okay. Now in this, look at first term is more than the second term, second term is more than the third term is more than the fourth term, like that. So indirectly a1 is more than or equals to a2 is more than or equals to a3 is more than or equals to a4, and up to so on. And so therefore nth term is more than or equals to its next term n plus 1 term. So therefore the sequence is said to be, therefore the sequence an, which is 1 upon n, is decreasing sequence. It is decreasing sequence. Decreasing sequence. Okay. Similarly, second one. So the first one and second one. So sequence 2 raised n. Sequence 2 raised n. Now what are the terms of the sequence? So if substitute n is 1, you will get 2, next 2 raised 2, next 2 raised 3, next 2 raised 4, next 2 raised 5, and up to so on. So now here, what is the observation now? So clearly a1 is less than or equals to a2, right? a2 less than or equals to a3 is less than or equals to a4, and up to so on. So this pattern is following. So therefore I can say that an is less than or equals to an plus 1. It is true for all n belongs to natural number set. So therefore the conclusion is sequence 2 raised n is running from 1 to infinity, is increasing sequence. Increasing sequence. It is an increasing sequence. Okay. So similarly, third one is this third sequence n, sequence n, just n. So this is here also. So now what is the first term? 1, second term is 2, third term is 3, and fourth term is 4, and fifth term is 5, and up to so on. So it is also same. What kind of sequence it is? It is increasing sequence. Directly I am writing. It is increasing sequence. Okay. What about fourth one? Let me do here itself the fourth one. Look at the fourth one, which is minus 1 whole raised n. Okay. This is a sequence. Sequence always need to write in flower brackets. Yeah, if you substitute n is 1, you will get minus 1, 1, n is 2 is 1, n is 3, minus 1, 1, minus 1, 1, minus 1, and up to so on. Okay. Now this sequence, it is not following any of the pattern like this. A1 is more than or equals to A2, A2 more than or equals to A3, up to so on, or A1 less than or equal to A2, A2 less than or equal to A3, up to so on. So it is not following any of the pattern perfectly, because look at minus 1 is less than 1, but 1 is not less than minus 1, right? 1 is more than minus 1. So it is not following strictly one pattern, either this one or this one it has to follow. So therefore directly I can say that, therefore the sequence is, so this minus 1 whole raised n is neither increasing nor decreasing. Neither increasing nor decreasing. Neither increasing nor decreasing. Okay. Since an, it is not less than or equals to an plus 1. It is not true for all n. Okay. And an is not more than or equals to an plus 1 for all n. For all n, it is not satisfying. That's why it is neither increasing nor decreasing. Now let us come to the monotonic sequence. A sequence of real numbers is said to be a monotonic sequence. Monotonic sequence if it is either decreasing or increasing. Okay. Look at the first sequence, it is decreasing. So therefore this is a monotonic sequence. So this is monotonic sequence. Second one, it is increasing. Therefore this is monotonic sequence. Third one, it is increasing. Therefore this is monotonic sequence. Fourth one, it is not increasing nor decreasing. Therefore it is not a monotonic sequence. Either it has to increase or decrease. Such sequences are said to be monotonic sequences. Yeah, look at this. Think over this and answer these questions. What is the greatest lower bound? That means GLBs. Greatest lower bound, GLB. That means what? Infimum. Okay. Indirectly, or one more terminology is infimum. Infimum. Okay. Question is asking about infimum. What is the infimum or greatest lower bound of an increasing sequence? Can you guess? So n is increasing sequence means, so a1 is less than or equals to a2 because it is increasing sequence, right? a2 less than or equal to a3 for all n belongs to natural number set. For all, it has to be true for all. So therefore such sequence an is said to be increasing sequence. And what is the greatest lower bound? Obviously the greatest lower bound will be the a1. Look at this is the lower bound for all. So therefore can I write a1 is less than or equals to an for all n belongs to natural number set. Can I write? Look at, so here my small m is like a1 now. So it is a lower bound. Small m is a lower bound, and that is particularly greatest lower bound. Okay, therefore, so therefore, here infimum or greatest lower bound or infimum is simply a1. So this is the infimum of an increasing sequence. Okay, it has to be true for all n. If you substitute n is 1, what do you get? a1 less than or equal to a1, true. And n is 2, a1 less than or equal to a2. Look at this. Obviously a1 less than or equal to a3. If you substitute n is 3, a1 less than or equal to a3, n is equal to 4, a1 less than or equal to a4. Look, this is obvious. Look at here, a1 less than or equal to a4. So for all these terms, a1 will be the lower bound. Okay, so that's what I have written. For all n belongs to natural number set, I can say that all of the terms of the sequence is bounded below by a1. So therefore lower bound is a1. As you know, lower bound is not unique. You can say any of the number which is less than a1 is also a lower bound. Okay, you take for example alpha is less than a1. For example, alpha less than a1, alpha less than a1 for example. Then I can say that alpha less than or equal to an for all n belongs to natural number set. I can say this one also. Therefore, I can say that alpha is a lower bound. Alpha is a lower bound. Lower bound. But what I want a greatest lower bound, infimum. So I need to correct all the lower bounds. In that, the greatest one I need to pick up. The greatest one obviously a1. So greatest lower bound will be the first term of the sequence. Okay. And similarly here, now what is the least upper bound of a decreasing sequence? Decreasing. So a1 more than or equals to a2. A2 is has to be 2 for all n belongs to natural number set. Right. Now in this, so I want least upper bound or supremum. Okay. Okay. So now each and every, so in this, what is the highest term? Highest term will be a1. So now I can say that an is less than or equals to a1. a1 will be the highest term of all the terms. So for all n belongs to natural number set. Now let us substitute n is 1, a1 less than or equal to a1. True. N is 2, a2 less than or equal to a1. Obviously, this is true from here. And n is 3, a3 less than or equal to a1. Yes, it is true. So therefore, first term will be the highest term. Therefore, that will be the upper bound. But more precisely, I want least upper bound. Right? Least upper bound means I need to collect all upper bounds. I need to collect all upper bounds. In that, I want the least one. So that obviously a1. So therefore, here my capital M can be taken as a1. Okay. So therefore, least upper bound LUP, least upper bound or supremum. Okay, or supremum, whatever. Supremum is what? A1, first term of the sequence. If it is decreasing sequence. So there's two observations. So based on this, let's have a theorem. Theorem number 5. The increasing sequence theorem. So remember here, increasing or non-decreasing, both are same. Look at, that's why I used here the terminology. Don't confuse with the terminology. Non-decreasing means increasing only. Don't confuse with the terminology. So now an increasing sequence of real numbers converges if and only if it is bounded above. So look at the proof. Observe carefully. The proof goes on cleverly. Understand each and every line. Yeah, let us focus. First, what is it? Since it is if and only if statement, first I want to take the LHS part. By taking LHS part, I will prove RHS. Okay. Now, what is LHS? Given that A is an increasing sequence, so let sequence AN be an increasing sequence. Next, what do you would assume? And which is converges, right? An increasing sequence of real numbers converges, and sequence AN. See, sequence means sequence of infinitely many numbers, infinite sequence of real numbers. Just I am telling just sequence. Sequence means infinite sequence of real numbers. That assumption I made in the first class only. Okay. Now, and the sequence AN converges to L, let's say. Okay. So this assumption I have taken. Because look at the LHS part, an increasing sequence of real numbers converges. So first of all, I have taken A and B an increasing sequence, and this is converges to L. Then we have to prove that. Then we have to prove that sequence AN of real numbers, what I need to prove, it is bounded above. N is bounded above. So this we have to prove. Bounded above. Okay. This we have to prove. That means I have taken LHS, this part is LHS part and this one is RHS part. So this one you have to prove. Okay. Now let us proceed. So what is given to us? A and B an increasing sequence it is given, and also it is converges to L is given. So overall what I can say is a converging sequence is given to us. But you look at from theorem number 4. What is theorem number 4? From theorem number 4, every converging sequence is bounded, right? So this is theorem number 4. I proved it. Every converging sequence is bounded. Look at here, AN is a converging sequence only. Therefore, obviously it is bounded, right? So therefore, the given sequence, AN is bounded. That's it. Bounded by theorem number 4. So AN is bounded. So therefore, once it is bounded, therefore there exists some M belongs to real number system such that AN less than or equals to M for all n belongs to natural number set. So therefore the sequence AN is bounded above. Actually it is bounded means it is bounded below and bounded above. Particularly what I want to prove, it is bounded above I need to prove. So obviously it is bounded above. AN is bounded above. That's it. So proof is over. One way proof is over from LHS to RHS. Next you take RHS part, then you prove LHS1. So what is RHS1? You take a bounded above sequence, just a bounded above sequence. That means only this one you have to take, AN less than or equal to M for all n belongs to natural number set. So you take this statement as assumption, then you have to prove that it is converges. So first one, what kind of sequence you have to take? An increasing sequence you have to take. Increasing sequence which is bounded above you have to take. Increasing sequence which is bounded above you take. Then you prove that sequence is converges. Okay. Now let us take that. So other way of proof, that means you take RHS part, then prove it LHS statement. Okay. So let AN be an increasing sequence bounded. Then we have to show that sequence AN is converges. So this we have to show. Okay, this we have to show. So then use AN is increasing and bounded above. So therefore given that, listen this part carefully. So given that AN is bounded above, so AN is bounded above, that implies AN is less than or equals to M. Some M exists such that all n belongs to natural number set, AN is less than or equals to M, since it is bounded above and it is increasing, right? It is increasing. So that too you have to take, then you have to prove it. The given sequence is converges. Okay. So here, can you say that M is the least upper bound? Think over it. So let's say that M is a least upper bound, LUB. I'm taking this m is a least upper bound. Once it is bounded above, then compulsory least upper bound exists. Assume that least upper bound is m. Okay. Then here my m is least upper bound. So now you look at here. See, listen carefully. So let's say, so this is my m. Okay, this is my m, and this is my m minus some epsilon, for example. M minus epsilon, some epsilon is positive. I subtracted that epsilon from m. Obviously m minus epsilon is less than m only. Okay, so look, assume somewhere m minus epsilon is here. Now the terms of the sequence a1, a2, a3, a2 up to so on, all these are lying here, and all the terms of the sequence are less than or equal to m. That means this is a least upper bound. Let's say this is a least upper bound, and all the terms are bounded above by this capital M. Okay, now can I say that this m minus epsilon, is a least upper bound? Does it become a least upper bound? First of all, it cannot be a least upper bound, because least upper bound, if it exists, it is unique. Already we discussed it. Okay, see, for example, you don't know that the least upper bound is unique concept, you don't know. Then how to prove that m minus epsilon is not a least upper bound in this case? Because already I assumed that m is a least upper bound. Now I am asking, can it be a least upper bound? Can it be a least upper bound? So for example, if it is a least upper bound, okay, if it is a least upper bound, then what I can say, if m minus epsilon is a least upper bound, if m minus epsilon is least upper bound, then I can say that an is less than or equals to m minus epsilon, because this is a least upper bound. What is in the least upper bound? You need to collect the upper bounds. In that, the least one is m minus epsilon. So therefore, this is upper bound only, but least one. Now each and every term of the sequence is bounded above by m minus epsilon. Okay. So, but this is contradiction. Why? Because I have taken m is the least upper bound. So that is contradicts. Therefore, m minus epsilon cannot be a least upper bound. So once m minus epsilon cannot be least upper bound, then the terms of the sequence, for example, a1 is the first term, a2 is the second term, a3 is the third term, a4 is the fourth term, up to so on. All these are the terms of the sequence, let's say. Okay. Now, can I write some number of the sequence? Let's say a capital N. Can I say that this a capital N, that means one of the term of the sequence, can I say that this is more than m minus epsilon? That means there exists at least one term between m minus epsilon to m, because m minus epsilon is not a least upper bound. Okay, if m minus epsilon is not a least upper bound, definitely there exists a term which is more than m minus epsilon. For example, such term an does not exist. Such term an does not exist. That means what? All the terms are below m minus epsilon. Then I can say that m minus epsilon will be least upper bound. But here L minus epsilon is not a least upper bound, right? I have taken m will be the least upper bound. So therefore, compulsory one term will exist in between m minus epsilon to m. So there exists one term an. Is it clear? Look at once again I am telling. Now I have taken m will be the least upper bound. Least upper bound means compulsory all the terms are less than or equal to that number m for all n belongs to natural number set. Now I am taking one more term m minus epsilon, which is obviously less than m only. Okay. Then what I am saying, I am taking this one. An is more than m minus epsilon. That means what? There exists a term from the sequence which is more than m minus epsilon. More than m minus epsilon. I have taken a sequence an, a term an which is more than m minus epsilon. Here what is my question is, does an exist which is in between m minus epsilon and m? Obviously yes, exist. For example, if such a term an does not exist between m minus epsilon to m, what happens in general? That means, therefore, all the terms are below m minus epsilon only. If such a term does not exist here, all the terms means what? A1, A2, A3, up to so on. All these terms are below m minus epsilon. Therefore, now m minus epsilon become least upper bound. But that is contradiction. I have taken m will be the least upper bound. So because of that reason, definitely there will be a term from the sequence which is more than m minus epsilon. So therefore here what I can say is, so therefore there exists there exists a term an for some n, capital N, such that what I can say, m minus epsilon is less than a capital N. After m minus epsilon, such a term exists. So this is one of the term of the sequence which is more than m minus epsilon. Okay. So call this is some 1. Now, what kind of sequence we are taking? It is an increasing sequence, right? So since, observe this, so since an is increasing, sequence, so therefore a capital N, look at a capital N is one of the term of the sequence, right? So that will be less than or equals to an for all n more than or equals to capital N. That means what? After the index n, see after n only, right? That means what? N plus 1, capital N plus 1, capital N plus 1, capital N plus 2. Okay, so all these are the indexes. Okay, n plus 3 like this. So all these are more than capital N. So small n takes n plus 1, n plus 2, n plus 3. That means what here? N plus 1, n plus 2, n plus 3. So all these are more than an only, since it is increasing sequence. a1 less than a2, a2 less than a3, a3 less than a4 like that, right? So this is obvious. Okay, let's say this is number 2. So from 1 and 2 I can say that from 1 and 2 I can say that m minus epsilon less than a capital N, but this is less than or equals to an. Okay, this is what for all n more than or equals to capital N. So remember, actually what I want to prove, that should be very clear. Look at here, I will tell you what I want actually, what I need to prove is I have to prove that the sequence is converges. So according to converges definition, for all epsilon greater than 0, right? For all epsilon greater than 0, there exists natural number n such that, okay, there exists natural number n such that modulus of an minus l should be less than epsilon. This I need to prove. So once I am proving this, then I am done. The sequence is converges, because this is converges definition. So what is modulus of an minus l less than epsilon? It means what? So an will lies in the interval l minus epsilon to l plus epsilon indirectly. So if I prove this statement, if all the terms are lying in this interval, that means what? For all n more than or equals to capital N, right? If infinitely many terms lying in this interval n minus epsilon to l plus epsilon, then I am done. The sequence is converges. Indirectly I need to find the upper and lower bounds for the nth term, proper upper and lower bounds. And how many terms should lie in that interval? Infinitely many terms should lie in that interval. Then I am done. The given sequence is converges. So for that, because of that only, look at I am obtaining the upper and lower bounds. Indirectly an is bounded below by m minus epsilon. Indirectly lower bound I obtained already. So I need to worry about the upper bound. I need to struggle about upper bound. And upper bound is obvious because look at, already I have taken, given that an is bounded above, therefore an less than or equals to m. So therefore let's say this one, let's say this one is some number, this one is already 2 is over, let's say this is 3, third statement. So by using third statement, and let's say this is third one and this is fourth one. Okay, fourth one. So from third and fourth, what I can say is m minus epsilon less than or equals to an, but an less than capital M. So therefore what I can say, from 3 and 4, so from 3 and 4 from 3 and 4. M minus epsilon less than a capital N, okay, less than or equals to a n, and this is less than or equals to capital N. That's it. And obviously I can say that, so therefore I can write for an, look at for an, what will be the lower bound? An will be the lower bound, and m minus epsilon also a lower bound. So now can I write an having lower bound is m minus epsilon. So an having lower bound m minus epsilon, at the same time am having upper bound m, and m is strictly less than m plus epsilon, right? We are adding, so for some epsilon positive, okay. So let me write here for some epsilon positive. So here I can say that, so let me write here for epsilon more than 0, some positive epsilon I have taken. For that positive epsilon more than 0, this is true, okay. So here, so for that positive epsilon, obviously m plus epsilon is strictly more than m, okay, because epsilon is strictly more than 0. If it is more than or equal to 0, it will be equals, right? So therefore clearly I can say that for nth term of the sequence lying in the interval m minus epsilon to m plus epsilon, okay. Epsilon. This is for what? Is it for all n? For all n more than or equals to capital N only. Why? Because it is not true for all n. It is only true for n more than or equals to capital N only. N more than or equals to capital N. Okay. After capital N means n plus 1, n plus 2. Look at here, I have written already. N plus 1, n plus 2, n plus 3. For this term only, for this index terms only, this inequality is true. That means for all n more than or equals to capital N. So that way this statement is true for n more than or equals to capital N. So therefore this I can write as in symbolic form. So therefore an minus m less than epsilon for all n more than or equals to capital N. So therefore all this together I can say that, so therefore final statement is, so therefore for epsilon positive, for epsilon more than 0, there exists, okay, there exists a natural number n belongs to natural numbers such that what we got, modulus of an minus m less than epsilon for all n more than or equals to capital N. So therefore the sequence an is converges to here instead of L you have m, right? Converges to m. That's it. Therefore what I want to prove, an should converge, that's it. It is converges to which number we don't want. I want whether it is converges or not. Yes, it is converges. So therefore an is converges to m. Therefore the sequence an is converges. So hence proved. That's it. So therefore here one note you have to make. So therefore what we observed in this theorem is, so every increasing sequence, so I need to show that this is a subsequence of 1 upon n. First of all, what is a sequence? So sequence 1 upon n, sequence 1 upon n. Now what are the terms now? 1, 1 upon 2, 1 upon 3, okay, 1 upon 4, 1 upon 5, 1 upon 6, 1 upon 7, 1 upon 8, 1 upon 9, 1 upon 10, and up to so on. Now the another sequence is 1 upon n factorial. Substitute n is 1, 1 by 1 factorial is 1, n is 2, n is 2, 1 upon 2, n is 3, so 3 factorial is 6, 1 upon 6, n is 4, 24, right? So 1 upon 24 and up to so on. So this is about this sequence. So now we need to conclude this one is a subsequence of 1 upon n. So obviously look at here, one, see, if I want to conclude this one is a subsequence of this one, in general how to get subsequence, the terms of the subsequence are not new terms, they are old terms only, but according to some order or some rule we'll collect the terms from the sequence only. Look at first term is this one, so this is the first term, this first term you are collecting from here, so second term you are taking from here, third term you are taking from here, like this. So this is the third term, like this. Somewhere you will get 1 by 24 for n is equal to 24, and that term will be 1 by 24, like this. So in this few terms you will collect according to some rule, that rule is 1 by n factorial. Here 1 by n factorial will be the rule. According to this rule you are collecting the terms are like this. For example, there is a one term here, for example including all this, you are having a term like this. For example 0 you are taking, for example 0 comma 1 comma 1 by 2 comma up to so on. Do you find 0 here? Here there is no 0 term in the sequence, therefore this sequence is not a subsequence, because you are not collecting 0 from the original sequence. Okay, each and every term of the subsequence is a term of a sequence only. Hope you understood this. So therefore the terms of the subsequences are nothing but the terms of the sequence only but according to some rule. So clearly here what I can say is, so now here a n k, so it's like a n k, so this is like a n, so this is like a n, sequence a n, and this is like sequence a n k. Okay, sequence a n k. Okay, now sequence a n k is nothing but, so sequence a n k, if you run k from 1 to infinity, k from 1 to infinity, what will you get? You will get a n1, right? Next a n2, next a n3, okay, a n4, okay, and up to so on. So therefore clearly what is n1 here, can you guess? So therefore n1 will be the, so this is the first term, right? This is an1, n1 is nothing but here 1, that means here this is a1, this is a2, so all these are the terms of the sequence. Now a1 is becoming an1, right? A1, look at a1 is becoming an1, therefore what is n1? N1 is 1. Now what is an2? an2 is nothing but a2, okay, and what is an3? Third term is my 1 by 6, but what is that? a6, right? a6. So therefore n2 will be 2, and what is n3? n3 will be 6, so up to so on. So therefore I can say that n1 is less than n2, n2 is less than n3, and up to so on. So this condition is satisfying. Okay, so therefore what I can say, therefore sequence 1 upon n factorial be the subsequence of the sequence 1 upon n. That's it, simply. So remember, every subsequence is also a sequence only, but why special sub? Because you are obtaining it from a sequence only. This is a sequence, from this you are generating the terms for the new sequence. That such a new sequence is said to be subsequence, nothing else. So every subsequence is again a sequence only. Okay, next one. So therefore the given sequence 1 upon n factorial is a subsequence of 1 upon n. Look at the second problem. So many students are asking about this one, sir, how to conclude a subsequence or not. So first let us take a sequence an, which is 1 upon n. So here what I want is a subsequence or not, right? First let me look at the terms of the sequence. So 1, 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5, 1 upon 6, 1 upon 7, okay, 1 upon 8, 1 upon 9, and up to so on. So these are the terms of the sequence, right? Now look at the next one, what is the next one? So this is a question. Does this sequence is a subsequence or not? What is the first term? 1/3. Second term, 1/5. Third term, 1/2. Next, 1/7. Fifth term, 1/6. Next one, 1/10. So these are the terms of the one new sequence. Now, does it a subsequence of this sequence? That is the question actually. Is this one is a subsequence of 1 over n, right? Now, what is the first one? The fundamental fact is all the terms what you are taking should be the terms from the sequence only. Yes, 1/3 here, 1/3. Look at it. So 1/3. This is 1/3. 1/5. Yes, you are collecting 1/5, and 1/2 you are collecting here. This is 1/2. 1/7, 1/6, 1/10. Yes, each and every term is from sequence only. The next one has to satisfy n1 less than n2, n2 less than n3 like that. So that has to be satisfied. So this is an1, right? This is an2. This is an3. This is an4, an5, okay, and an6. Okay. Now look at here. an1 is nothing but 1/3, right? But this is nothing but what? Here 1/3, which term here? So now this is a1, this is a2, and up to so on. Okay, up to so on. Now an1 is nothing but 1/3, but 1/3 is nothing but a3 here, right? This is a3. So therefore, clearly, what is n1? n1 is 3. So likewise, what is n2? That means an2 will be 1/5 here. 1/5 means it is a5. So therefore, n2 will be 5. Next, what is n3? 1/2. 1/2 is nothing but a2. So therefore, it is 2. What is n4? n4. an4 is 1/7. 1/7 is nothing but a7. So it is 7. Next, an5 is 1/6. So therefore, it is n5 is 6. So up to so on. But here look at, is it satisfying n1 less than n2 less than n3? This condition, it is not satisfying. Look at n3 less than n4, n4 less than n5, n5 less than n6. Does it satisfying? Check once. Look at here. Clearly, 5 n2 is not less than look at n2 is not less than n3. n2 is 5. Look at here. n2 is 5. Let me write here. n1 is what? 3. 3 less than n2. What is n2? 5. Less than, should be less than 2. Should be less than n4 is 7. Should be less than n5. n5 is 6. Does it true? It is not true, right? Look at here. This is wrong. And here 7 is not less than 6. So it is also not true. Therefore, this condition is not verified. So therefore, conclusion is the sequence 1/3, 1/5, 1/2, 1/7, 1/6, 1/10 is up to so on. Sorry, you write up to so on because sequence means it is infinitely many terms. Okay, up to so on is not a subsequence. Not a subsequence of original sequence 1/n. So this condition also must be satisfied. Okay. Next one. Problem number 3. Yeah. Does the sequence show that the sequence is bounded? Bounded means upper and lower bound should exist. Its nth term. Rule compulsory required. Without rule, we cannot find or we cannot generate the terms of the sequence. So now what is a? So first term is a1, second term is a2, third term is a3, fourth term is a4, and fifth term is a5, and up to so on. Then accordingly, the terms are a1 is what? 3/2. a2 is -4/3, right? And a3 will be 5/4, and a4 will be -6/5, and up to so on. So these are the terms of the sequence. So if I substitute n is 1, I should get this. That is a1. If I substitute n is 2, I should get -4/3 like that. So therefore, clearly, what is nth term? Let's guess the nth term. First, you forget about the negativeness, minus symbol. So if I substitute n is 1, denominator I should get 2. So therefore, n plus 1 obviously. If I substitute n is 1, what I will get? Here 2. Look at like this. Same thing, if a substitute n is 1, you should get here 3. So therefore n plus 2 here. That's it. Now substitute n is 1, 3 by 2. N is 2, denominator 3, numerator is 4. Perfect. Forget about this minus, I will take care of that later. Next, n is 3, 4 to get 5 by 4. Perfectly alright. Now let us look at the sign. Okay. What I want here, if I substitute n is 1, you should get positive 1. So minus 1 whole to the power of, let's say n minus 1 you take. Okay. Let me write this clearly. So minus 1 whole to the power of, minus 1 whole to the power of n minus 1, n plus 2 by n plus 1. So this will be the nth term. Now substitute n is 1, n is 2, n is 3, and this term can be generated. So therefore now the sequence is, what is the sequence? Sequence an is, it will be minus 1 raised n minus 1 or n plus 1, whatever your wish, n minus 1 into n plus 2 divided by n plus 1. So this is a sequence. Then if you run the sequence, n is from 1 to infinity, you will get these terms. Okay. Now how to show that it is bounded? That means what I need to show that there exists small m and capital M such that I need to show that m is less than or equals to an, which is less than or equals to m. This I need to show. Then I am done. The sequence n is bounded sequence. That means upper and lower bound should exist. That I need to prove. Now let us take an, the nth term of the sequence an, which is minus 1 whole raised n minus 1. Okay. And n plus 2 upon n plus 1. Okay. Now let us take the modulus on both sides. All these are tricks, okay, how to show that a sequence is bounded. Okay. So now this will be, so since it is modulus, negativeness will go, so modulus of n plus 2, I can write n plus 1 I can write upon n plus 1. Okay. And this will be modulus of n plus 1 is a one term and 1 is another term, second term. So n plus 1 divided by n plus 1 is 1 plus 1 by n plus 1 I can write. Can I write? So consider this one is one term, n plus 1 is one term, and this is another term. So n plus 1 divided by n plus 1 is first term, that is 1. Next place 1 by n plus 1. Okay. Now look at what is n? N is the index which is from 1 to infinity. If you substitute n is 1, what will you get? 1 by 2 here. We'll look at only this one, not this one. Forget about this. Look at this one. Substitute n is 1, you will get 1 by 2. N is 2, 1 by 3. N is 3, 1 by 4, 1 by 5, 1 by 6. Then what is the last term? For large number of n, you will get 0. So therefore this quantity is not more than 1. So therefore obviously this entire 1 plus 1 over n plus 1 is less than or equals to 2, I can write. Upper bound. Okay. Since 1 upon n plus 1 is always less than 1 only for n belongs to natural number set. Okay, n belongs to natural number set. You take whatever n from natural number set, substitute here, that will be always less than 1 only. So because of this reason, so this is always less than 1. This is already 1. Therefore, if you do sum, this will be less than or equal to 2. This particular, not for, see, this is true for each and every n. Okay. So therefore, finally what I got, modulus of an is less than or equals to 2 I got. Okay. So therefore modulus of an is less than or equal to 2. Therefore I can write minus 2 less than or equals to an less than or equals to 2 if you remove the modulus. So this is true for all n belongs to natural numbers. That's it. I proved. Look at. So therefore the sequence an is nothing but what? The given sequence, this one. So this one. So this one an is bounded sequence. Bounded sequence. One upper bound, one lower bound should be required. That's it. So any number more than 2 is also an upper bound. You can write this one as minus 3 less than n less than 3 also. That is also true. Okay. Therefore the given sequence is bounded sequence. So this is a way of showing the given sequence is bounded. And the last problem, look at this one. is the sequence an, which is defined by this, is bounded above. That means what? Bounded above means given sequence is an, therefore an is less than m. I need to show like this. There exists such m such that it is true for all n belongs to natural number set. Then I can say that the sequence n is bounded above. Not asking, it is bounded. Bounded means I need to show n lies from minus small m to plus m. So previous problem, small m is minus 2, capital M is plus 2. Then I can say that that is bounded sequence. Here I need to show it is bounded above. Bounded above means only upper bound is required, that's it. So I need to show that there exists a m such that n is less than m. This is enough. Okay. First you generate what is the sequence first. Okay. So this is a recursive sequence, right? So an plus 1 is the square root of c plus an. Now if you substitute n is 1, substitute n is 1, what you will get? a2. What is a2? Square root of c plus n is 1, I am substituting c plus a1. Now this will be square root of c plus, what is a1 now? a1 is root c. Look at, this is the initial term. Look at, a1 is root c. Okay. Next n is 2. Substitute here n is 2. You will get a3, third term of the sequence, square root of, substitute n is 2 here, c plus a2. Okay. Now this is nothing but c plus, what is a2? a2 means, look at the previous one, a2 is nothing but root over c plus again root over c. Okay. So this is third term. So if I substitute n is 3, what will you get? Substitute n is 3 here in this recursive formula. N is 3, will get a4, fourth term. So c plus n is 3, I am substituting a3. So what is a3 now? a3 means this one. So therefore finally this is square root over c plus square root over c plus square root over c plus root c. Okay. So therefore this is c4, a4. So therefore finally it will be so therefore the given sequence an is to so on. So this is nothing but a1 is root c, which is positive, next to root over c plus root c, this is a2, this now we form, and a3 is c plus root over c plus root c. Okay, this is a3. Next a4, c plus root over c plus root over c plus root c. Okay, this is c4. That's it. So this is up to so on. So like this. So these are the terms of the sequence. Now I need to show that it is bounded. So by induction I want to proceed. So by induction, by mathematical induction, by mathematical induction, hope you know this. First I need to prove that the given statement is true for n is 1. Let me quickly recall here. First I need to take I need to prove that n is 1. I have to prove it, right? I have to prove this. N is 1, it is true. Next I have to assume that n is equal to some k, it is true. This is the assumption. Okay. Next I need to prove that n is equal to some k plus 1. We have to prove this one again. Then I can say that for all n it is true. So this is the final comment. Therefore for all n the given statement is true. So this is mathematical induction. Actually how what happens behind the screen is, see, now I am proving n is 1, the theorem is true, right? If n is 1, the theorem is true, then we are assuming n is k, the theorem statement is true. Next we are proving that n is equal to k plus 1, the theorem statement is true. That means you are proving n is equal to k plus 1. That means what? Already n is equal to k, but what is n value? N value is 1. Therefore substitute n is 1 here. What will get k value? K should be 1. K should be 1, right? Substitute k value here. What will get? 1. 1 plus 1, 2. Indirectly you are proving n is equal to 2. That means n is 1, the theorem statement is true. N is equal to 1, the theorem statement is true. You proved. Now you are proving that n is 2, the theorem statement is true. Now n is 2, the theorem statement is true. Now let us come back again. It is a loop statement. Now n is equal to 2. Let's substitute n is 2. N is 2, it is true. That means what? K value is 2. So K is equal to 2, it is true. Substitute here, K is 2. Indirectly you are proving that N is equal to 3. So like that you are proving for all values of N indirectly. So indirectly the theorem statement is true for all the N. So this is the mechanism behind mathematical induction. Now you look at here. First I want A1. Okay, look at here. I want A1. What is A1 here? A1, which is root C. Look at the first term, root C, right? So root C is obviously less than C. If you take C is 1, then it will be less than or equals to, but this is strictly less than C plus 1. This is true, right? A1 is less than C plus 1. So therefore I can say that A1 less than C plus 1. Okay. For this particular sequence, A1 is less than C plus 1. Indirectly, first term is bounded above by C plus 1. You need to prove that all the terms are bounded above by some number m, right? Look at here. Top right, an less than m. I need to prove that for all n, but I am taking for particular n is 1, I proved here. I have proved for n is 1. So since I am proceeding by induction, A1 is less than C plus 1, n is equal to 1, the theorem statement is true. See, it is true for all n belongs to natural number set, right? That means what? N is 1, n is 2, n is up to so on. Now first n is 1, I proved already. N is 1, I proved. Next one, what? I have to assume n is equal to k. So assume, next one, assume for some m belongs to natural number set, am less than C plus 1. I am assuming this. Listen carefully. First of all, this is the fundamental statement what I want to prove actually. What I need to prove actually. An should less than m for all n belongs to natural number set. Then I can say that the sequence is bounded above. Okay. Now if I substitute n is 1, a1 less than m, n is 2, a2 less than m, n is 3, a3 less than m, like that. First I am proving for n is 1 is equal to, I proved already. So therefore a1 less than C plus 1, I proved this one. Okay. So now 1 is true. For n is equal to 1, it is true. Next assumption is for n is equal to, I am taking some m. So I am assuming for some m belongs to natural number set, am is less than C plus 1 is true. Is true. Next we have to prove that, then we have to prove that am plus 1 is less than C plus 1. That what, right? N is equal to, k is assumption, I need to prove that n is equal to k plus 1. Same like. Okay. N is equal to m, I assumed it is true, then n is equal to m plus 1 I need to prove. So I need to prove this statement. So look at in this, assume from second statement, assume this is statement number 1. So from 1 implies am less than C plus 1, right? Now I am writing C plus am now. I am adding both sides C plus C plus 1. Then what will you get? C plus am is less than 2C plus 1. Okay. Now I am taking square root both sides. Square root over C plus am is obviously less than square root over 2C plus 1. Okay. Yeah. So now can I write square root over C plus am, okay, less than square root over 2C plus 1, but can I write this is less than now? This is the main step, listen carefully. This is 2C plus 1, can I write this is less than square root over C square plus 2C plus 1. Can I write this one? I cannot easily, because here just to 2C plus 1, but extra C square is included. Therefore, obviously this number is more than this number. So what is the difference between these two numbers? Square root over 2c plus 1 is less than square root over c square plus 2c plus 1. c square one number you added extra. This is positive number. Okay. Look at here in the question only, root c is positive. Then if you square it, you will get c, right? That is obviously positive. So look at c square. Again square it, it is positive. So adding one positive number. Therefore this become more. Now look at here. Square root over c plus am, okay, less than square root over this. I can get c plus 1 whole square, right? I think now you understood why I have added c square extra. Now root and square cancel out. Then what will get? Square root over c plus am is less than c plus 1. Okay. But what is root c plus am? Look at the question now. Look at this one. an plus 1 is equal to root c plus an. Substitute n is equal to m here. Then what will you get? am plus 1 value root c plus am. So root of c plus am is nothing but am plus 1. am plus 1 is less than c plus 1. Now look at, am I got or not? Look at this one. I got am plus 1 is less than c plus 1. I got fine. Look at am plus 1 is less than c plus 1. Therefore, by induction, by mi I am writing. Mi means mathematical induction, not Redmi phone. Mathematical induction. By mathematical induction, it is true for all n. So therefore conclusion is, therefore the given sequence is bounded above. That's it. So here initially I have taken a1 less than c plus 1 and mth term also less than c plus 1, then m plus 1 term also less than c plus 1. Therefore for all n, an is less than or equal to cn plus 1. Therefore for all n means what here? So therefore an less than c plus 1 for all n indirectly. So this is a final statement. Therefore the given sequence is bounded above. So n less than c plus 1. So here my capital M is c plus 1 indirectly. My capital M is c plus 1. Look at here. That too I need to prove here. Look at top right. So I need to prove n less than some m. Then I can say that the sequence is bounded above. So clearly I have done that. N is less than c plus 1 for all n. By induction I proved it. Therefore the given sequence is bounded above sequence. And with this I will stop. I will do more number of problems in next class.